thanks, Bhargav. Thanks to everyone for coming and for the invitation to speak here. So what I want to talk about today is the following theorem that, well, as Bhargav just said, most hyperelliptic curves over Q have no rational points. So I'm going to try to sketch the proof of this, but maybe before I do that, I should make more precise what I mean by this. So by hyperelliptic curve over Q, I mean a nice curve, so a smooth, geometrically reducible, complete curve that has a fixed degree 2 map to P1, where everything's defined over Q. So in particular, so more concretely, that means that any hyperelliptic curve over Q can be expressed by an equation of the form let's say call it C. So C can always be expressed in the form z squared equals f of xy, where f of xy is a homogeneous polynomial in x and y of degree n, say. So I'll always write it in the following way. So f0 x to the n plus f1 x to the n minus 1y plus fn y to the n. So where n is given by 2g plus 2, so g here is the genus. So the most concrete way to think about the genus is if you graph this, the solutions to this over the complex numbers and say weighted projective space, then you'll get, well, if you graph it in, well, you can think of it as if you set y equals 1, it's an affine curve, and if you set x equal 1, it's an affine curve, and it has the obvious patch. Y to the n minus 2. Oh, I see. Well, if you think of this in weighted projective space, so say with weights 1 and n over 2, then you get a good curve. Or you can put y to the n minus 2 here and then take the smooth completion. Okay, so where n is 2g plus 2, and you can always scale so that you can scale your solutions so that the fi are in z. And if you're to be smooth and geometrically reducible, then this polynomial will have distinct factors over q bar. Okay, so I'm going to take my models for hyperelliptic curves over q of this form, and then we can define.
But if you wrote what I would call y, z squared is a monic polynomial of degree 2g plus 1, so it visibly has a point. So somehow those don't count in this.
That's right. Yeah. Right.
You'll explain
the
counting that makes them disappear.
Yeah, I will. Yeah. Right. So the family you're talking about is special. It has a rational Weierstrass point. Right. But the generic set hyperelliptic curve will not. But we can look at that family separately as well, and I'll do that. So, okay. So then define the height of the curve C. So we'll call it h of C. So that'll just be the maximum of the absolute values of the coefficients of the binary form that's giving us our hyperelliptic curve. So we've chosen our fi to be in Z. And now we can sort of go across all hyperelliptic curves over Q ordered by this height. And then the theorem maybe I'll move this up and I'll state the theorem there. So the theorem is then that when you order so the theorem is that when all hyperelliptic curves C over Q of genus G are ordered by height, a proportion of at most O of e to the square root of g over log square root of g minus, sorry. That's important. Of them possess a rational point. So in other words, if you look at curves of bigger and bigger heights, so say height in a height less than x, and as x goes to infinity, you look at the upper density of the hyperelliptic curves that have a rational point, then as the height goes to infinity, you're going to get a proportion of at most this. And so in particular, so the point is that, so this bound comes from bounding certain real and p-adic integrals, and it can almost certainly be improved. In fact, I mentioned it to Terry last night because I thought the integrals were quite pretty. He got very interested, and I had 7 emails from him this morning. And so I suspect in the next few days this bound will improve drastically. But given that, but the point is that this is going to 0 very quickly with g, even more quickly than it says there, probably. And so, yeah, n fixed or g fixed, same thing. Yeah. G can be 1, and the proportion comes out to be positive. So yeah, I'll mention that in a sec. So the corollary is that as g goes to infinity, a density approaching 100% and approaching exponentially fast, density approaching 100% of hyperelliptic curves of genus G have no rational point. So of course, Falting's theorem is relevant here. So once the genus is at least 2, then Falting's theorem says that any such curve has at most finitely many rational points. And there have been effective versions of Falting's theorem in the sense that there's an effective bound on how many points such a curve can have. I think the best known is 7 to the g. So the bound increases with g for a fixed curve. And what this is saying, but for a typical curve, can one do better than 7 to the g? And the answer is yes. For a typical curve, well, the typical curve has no rational points. That's what it's saying. And since a density, so this is something that's easy to see, is that a density approaching 100%. So since as g tends to infinity, a density approaching 100% of hyperelliptic curves, genus G over Q, have a point locally, so have points locally at every place of Q. What that also means is that, so as G goes to infinity, density approaching 100% of hyperelliptic curves. Right, for elliptic curves of genus G over Q fail the Hasse principle. Right, so and Mike, just to get to your question, so already for genus 1, one gets a positive proportion here, actually. Those are the methods that I'll talk about in a second. So for genus 1, proportion is positive. I can right now prove even about 20%. So 20% of genus 1 curves of the form y squared equals a quartic, at least 20% will fail the Hasse principle. And for genus equals 2, the proportion is already greater than 50%. So that's why I felt okay about saying most in the title, because it's true even for once you're an actual genuine hyperelliptic curve of genus at least 2, at least 50% don't have any rational point, even though they locally do.
Even
Yeah, so I only proved the lower bound. The right number, I would guess, would be 100%. That would be my guess. Yeah. So I think if you pick a random genus 2 curve, I think there's 100%. There should be a 100% chance that you don't have any rational points. But it wasn't known before that it was even more than 0%. And say you go, it's a genus at least 10. I was just working this out. You're already at 99%. So once your genus is moderately high, you're very close to 100% chance of not having any rational point. So in elementary terms, what we're saying is that we have a polynomial of this type, a binary form of this type. The chance that it takes a square is very small, especially as the degree goes up. Okay. Okay, any questions about the statement? So in the 1940s and 50s, there were these examples, the first ones given in the 40s and 50s of curves that failed the Hasse principle. So some were due to Lind and Reichardt. They were of the form y squared equals binary quartic. Those are the first ones. And then Selmer gave his famous 3x cubed plus 4y cubed plus 5z cubed example. And this is in some sense, those examples are not rare. If you really pick a random binary quartic, it has a fairly sizable chance that it will fail the Hasse principle. So those examples are actually very common. Sorry? Yeah, so the method actually allows you to prove it. And I'll show you. So the method actually allows you to prove it in many cases. And in fact, you can sort of show that you can prove it in this many cases fairly explicitly. Yeah. So here's the key construction behind the proof. So there's one sort of key algebraic construction. So, well, first of all, the key idea behind the construction is to use the representation. We use the representation Z2 tensor sim2 Zn of GLN. And we're particularly interested in the groups over Z. So I'll call this representation V. So these are the points of V of Z. I'll call the GLN G. So we're interested in this representation of G of Z on V of Z. And so the way to think of
it's two copies of sim2.
That's right. Yeah. So we view. So I'll view elements of V of Z as pairs AB of matrices, symmetric n-by-n matrices. With integer entries. So that's how to think of elements here. You just have pairs of symmetric matrices, n by n over Z. And so given such a V, think of it as A comma B. These are symmetric n by n matrices. You can define what I call the invariant binary form of V. So say f of V, f sub V of xy, is just defined to be the discriminant of the pencil of quadratic forms that A and B span. So in other words, fv of xy will be, so the discriminant, which is the same as saying minus 1 to the n over, so I'll always keep n even for now. Over 2 times the determinant. So what we do is we take A times an indeterminate x minus B times an indeterminate y. Take the determinant. That will be a binary n form, right? Because the determinant is degree n on n by n matrices. And the point is that it's GLN Z invariant, right? It's an invariant for the action of GLNZ because, well, the way GLNZ is acting, it replaces A by GAG transpose and simultaneously replaces B by GBG transpose. And so this determinant will stay the same because GLN is acting on both A and B simultaneously. So this is a GLNZ invariant. And in fact, the coefficients of FV generate, at least over the complex numbers, they generate the ring of invariance. The polynomial ring, right? Or the ring of polynomial invariance, I guess you can say. The ring of polynomial invariance for the action of GLNZ acting on V. And so this, the coefficients of this binary form are a complete system of invariance for this action. And so a natural question is, so here's a natural question is, given a binary form F, of degree n, when does there exist when does there exist, right, V equals AB in V of Z, right? So when does there exist a pair of symmetric n-bind matrices such that its invariant binary form is equal to that F, right? So given a binary form, when does there exist a pair of symmetric matrices such that its determinant gives you exactly that F? So such that F sub V is equal to F. So you might think that this is always possible. That's what I first thought when I looked at this. And then I couldn't find a general construction. And then I eventually was able to prove that there doesn't always exist. So the short answer is that not always. So that means some binary n forms are special. And I won't give a complete answer today of when it does exist, but I'll give you a sufficient condition, which is relevant to the theorem at hand, which is that if z squared equals f of xy, maybe I'll say such an AB exists, if z squared equals f of xy has a rational point. So if the curve given by this. So in other words, yeah, so if this equation has a solution with rational x, y, and z not all 0, then you can use that to actually construct an AB such that determinant of ax minus by is equal to f of xy. And so I want to describe that construction, because that's sort of the key behind the theorem. So the point will be that if you have a rational point on this hyperelliptic curve, you can construct such an AB that gives you that binary form. And then we'll show that by a counting argument that most binary forms don't have such an AB, and that's what's going to give the theorem. So, okay, so to prove the proposition, so we use the classification of orbits of G of Z on VZ. So we'll describe the orbits in terms of another algebraic object, and then we'll use that algebraic object to construct this particular orbit. So first, the algebraic objects that we're going to describe these orbits in terms of are certain orders in degree n fields. So suppose we're given an F binary form of degree n, And let's assume f has non-zero discriminant for now, although a lot of what I say can be carried over even when the discriminant is 0. So let's assume f has non-zero discriminant. And also let's assume that f0, the leading coefficient, right, is non-zero. Then you can use an algebra of degree n over q, namely you can let kf equal mod f of x1, say. And since f0 is non-zero, so I should just say I'm taking everything over z. Okay, so this is some. So inside kf, there is a natural lattice with basis. I'll tell you what the basis: 1, zeta 1, zeta 2, zeta n minus 1, where zeta I are integral elements, and which by integral I just mean they satisfy harmonic degree n equation over z. And what are these integral elements? They're, we'd find zeta. Let's just find zeta k is given by f naught. So maybe let's see. What I'll do is let's write this as q adjoin theta, make it easier. So theta is the image of x in here. Right? Integral elements. They satisfy monic polynomials. Okay, so this is a very special lattice inside KF. Call it. So let's call this RF. And so this is a lattice that was studied by Birch and Merriman in their study of the moduli space of binary n forms. So Birch and Merriman showed, in particular, that the discriminant of this lattice, RF, inside KF, the discriminant of this lattice, is the discriminant of f as a binary form. So that's already one very nice property that was very important in their work. It's used a lot in the study of binary forms over Z for years after that. And it wasn't noticed until fairly recently, 15 years ago. Theorem of Nakagawa, that RF, which is why I use the letter R, is actually a ring. It's actually closed under, so it's a ring. So you can actually multiply these things, and you're still in the linear span, the Z linear span of this as a ring. So that means it's an order, right? It's an order in KF. Can I? What do I do? Would you be able to see here or no? Yeah, I can. You won't. Or maybe I'll move it up. 2/3. Which 2/3? Down here? Oh, okay. Okay. Right there. Okay. So this RF is a natural ring inside KF whose discriminant, so it's an order inside KF whose discriminant is equal to the discriminant of F. So that already tells you it's a very natural object. And there are many other things you can do with it. For example, you can define the following. So define some more lattices. in KF. So for example, I'm going to define IF of K. This is going to have span 1 theta squared all the way up to theta to the K. And then we'll use zeta K plus 1 up to zeta n minus 1. Okay, so that's another lattice inside KF. And it turns out, so IF of K is in fact an RF module. So that's also something that you can check just by, well, you multiply elements of RF by this, and you find you end up back inside IF of K for each K. So this is for, let's find this for 1 less than or equal to K less than or equal to n minus 1, say. You can do for 0 too. IF of 0 is the ring. And one other thing you check is that if you let IF equals IF of 1, then IF of K is in fact IF raised to the K as an ideal, the kth power of the ideal. That's also true. That you can also just check. And these lattices also came up in works that used work of Birch and Merriman. They weren't noticed before that they were modules for this thing that was actually a ring. and that's very useful for reasons that I'll tell you in a sec. Maybe what I should say here is that, so these objects were studied very intensely, well, in the case of n equals 2 and n equals 3, in my thesis, to understand sort of variations of Gauss composition for these small rank rings. And in general, for general n, what Wood showed is that there are natural meanings behind all these constructions, namely RF. RF is just the ring of global functions. Because this is all, the way I've stated everything was very basis dependent. And it's actually very useful for the things that I'm about to do. But just so you know, RF has a natural canonical construction without these bases. Namely, it's the ring of global functions on the subscheme of P1 of Z. So cut out by, so you can do this over any base, cut out by F. And IF. So if you take so it cuts out endpoints in P1, and if you take the ring of global function on there, it's a ring of rank n over Z, and it's exactly this RF that was constructed by Birch and Merriman. And IF of K, well, is going to be a module for RF. And what is it? It's the pullback O of K, from P1 to the ring. So that's sort of the geometric meaning of these constructions. But for the purpose of what I want to talk about today, it's actually useful to have the basis description, and I'll tell you that why in a second. Okay, so in terms of all this terminology, so here's the theorem. So I should also note, so this only describes IF as a module, but in fact IF of K, right? It comes with a basis, naturally with a basis. Right? So it's more just an ideal, it's a based ideal. Okay? And so the theorem, which for general n was worked out in Melanie Wood's thesis, is that if you take the elements of Z2 tensor sim2n, that have a fixed invariant binary form F, okay, then those elements are in one-to-one correspondence with equivalent classes of pairs I, comma alpha. Okay, so equivalent classes. And I'll say what equivalence is. So first of all, what is I? I is an ideal class of RF. Okay, rank n, having rank n over Z. So it's is some lattice inside Kf that's an RF module. Okay. And alpha is an element of Kf star, with the relation that I squared is contained in alpha times IF n minus 3. And the norm of I squared is equal to norm of alpha times the norm of IF to the n minus 3. So one might think that this condition forces equality here, but that's not true because these IFs that we've constructed are not necessarily invertible ideal classes. And when you're not invertible ideal classes, then this condition doesn't mean that this is actually equal. But if you have such a weird thing happening where you have non-invertible ideals satisfying this norm condition, then you can construct such an element. And what's the map? How do you go backwards? So the way you go backwards, if you have this data over here, I didn't say what equivalence is. So I'll just say I alpha is equivalent to kappa I. Yeah, maybe I should say ideal. You're right. And then we'll say that these two things are equivalent if you multiply by kappa and kappa squared. Yeah. Yeah. And so the way to go backwards, so suppose you have the information over there, the way you go backwards is you take the coefficients of zeta n minus 2 and zeta n minus, well, I'll go the other way, zeta n minus 1 and zeta n minus 2. So that's how you'll get two symmetric matrices. And now I have to tell you a symmetric pairing, of which you'll take these two coefficients, and you'll get your A and B. And the symmetric pairing is what you do is you take 1 over alpha. You take the map 1 over alpha times. That goes from I cross I to IF n minus 3. Right, so the point is that when you multiply two things in I, right, this is a symmetric pairing multiplication of two elements in I. Multiply them in I, you end up in alpha times IF to the n minus 3. So you divide by alpha, you end up in IF to the n minus 3. And now you take remember, what is the basis of IF n minus 3? Well, the last two basis elements are zeta n minus 1 and zeta n minus 2. You take those two coefficients, and those give you your A and B. So that's how, if you have an object here, you get an A and B by just taking this map. Okay, so I wanted to bring this up because, okay, so how do you use this? So if you can construct elements over here, then that allows you to construct pairs of symmetric matrices whose determinant is equal to F. Okay, so let's look at the case n odd, because this works equally well for n even and n odd. So then the theorem is that there always exists. So maybe I'll see this as the theorem. There always exists A, B, pair of symmetric matrices that give rise to F as its binary n form. And so why is that? Well, we just have to produce the correct object on this side. And the correct object we'll take alpha equals 1. And we'll take I to be IF to the n minus 3 divided by 2. And using the fact that IF to the n minus 3 over 2 times IF to the n minus 3 over 2 is IF to the n minus 3, that'll give exactly, it'll give you equality here. So where did we use n odd? We used it to divide n minus 3 by 2. And that argument doesn't work when n is even. So, and in general, in fact, you don't always have an AB that gives you F in the even case, and that's why there isn't a uniform construction here. Okay, so maybe I can write here. Yeah. So okay, so what if n is even? So let's do the n even case. So as I said, you can't do it in general you can't have a general construction, but you can use some special information. For example, suppose F represents a square, and that's So that's the case we'll do. So suppose, okay, so f is a binary form of even degree, and suppose f represents a square. So with that loss of generality, so one reason why I've been writing Z2 tensor to Zn is to just remark that there's a secret action of SL2 also on this representation, which changes the basis of A and B. And by such a change of basis, so a lot of these things, a lot of the constructions respect that action. So in particular, suppose f represents a square without loss of generality, say by that SL2 action, we can assume that the last coefficient is a square, say c squared. Okay, so what we're going to do is we're going to try to use C to make an ideal. And so here's the construction. So what I'll do is I'll let alpha equal theta. Alpha is going to be theta. Okay. So remember, theta is the generator of that field kf. Let alpha equal theta, and we'll let I have basis c theta squared all the way up to theta to the n minus 2 over 2. And then zeta n over 2 all the way up to zeta n minus 1. And then it's an easy check. So the fact that I could take a square root here allowed you to get a square root of the norm on this side. It was really that you really needed that square root here. And then you just check that I squared is contained in theta times I f n minus 3. And norm of I squared is equal to the norm of theta times norm of I f n minus 3. And so that allows you to make an object here. And I can actually write down what the object is. So using the explicit basis of I. So theoretically, this already says that we're going to get some element, but I just worked it out. And you can actually write it down explicitly, and it's quite pretty. So using the basis of I, so I'll just show you the case n equals 6. Since you'll see the pattern pretty clearly from just that one case. So for n equals 6, so here's the matrix. In the top left corner, and then there's zeros for a while. 1, 2, 3. In fact, there's zeros everywhere for a while. This was a fun computation because it seemed like this should show the existence of an orbit, but until you write it down, it's sort of hard to be convinced. Here it is. So it's got 1, 1, f0, 1, 1, 0, 1. And then you get f1, f2, 0 here, f2, f3, f4. Oh, no, sorry. It's f1, f2, f3. F1, f2, f3. And the last line is f2, f3, f4. Okay, that's your A. And B is similarly sparse. But here's the key, is that you have, so everything's 0 up here. 1, C. So you get an F1 here, F2 here, F2, F3. And in the bottom right corner, you have a minus F5. Minus F5. And that's your B. And you can see how the pattern would continue for general even n. And if you check you find that minus the determinant of ax plus by, ax minus by, is equal to f. Maybe I'll write it out. So it's equal to f naught x to the n plus dot 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 plus fn y to the n. So first coefficient is pretty easy to see. You see f0, and you see the fn here, and you can see how it was very important in the construction that you had a square root of fn, so that this is actually an integer matrix. So that's the construction. So if f represents a square, then you get a pair of symmetric n-bind matrices, whose determinant gives you your binary form, f. Okay, so what remains then is to show that most binary forms of even degree don't have such an AB giving rise to f. And so the way to do that is to count. So the idea is to count all AB in VZ up to the action of G of Z, because we're only interested in orbits under G of Z. So if let's call this V, such that FV has, say, height less than x for large x, and then we'll let x go to infinity. We want to understand the asymptotics of that. So the way to go about this is what we do is we construct a fundamental domain in VR for the action of GZ. And then when inside the fundamental domain, if we look at the lattice points, then those will correspond to elements of VZ mod GZ. Right, we let GZ act on all of the real vector space, and then if you just look at the lattice points, those are the elements of V of Z. And the way to do that is, well, we take a standard fundamental domain for G of R mod G of Z. Let's say the ones that have determinant. Let's look at just the ones that have determinant plus or minus 1. Okay. And if we hit that with all elements of V of R, whose height is less than x, up to the action of GLN plus or minus 1 of R, then if we multiply, so we take such a fundamental domain inside GLN minus 1 of R, and then we make a fundamental domain inside V of R up to the action of this group, then you get a fundamental domain for the action of GZ on V of R. And what allows us to make a particularly nice fundamental domain in this product is that one can work hard to construct a set where this is compact. So this can be made a bounded set. So you can find, for all elements of VR with height less than x, you can find representatives for the action of GLN minus 1 of R that lie in a bounded set. So that the complication only arises in this classical object, namely GLN R modulo GLN Z. And this is not compact, but it does have finite volume. And so when you look at this thing, you get some region in this vector space V of R, which has dimension n times n plus 1. And the region kind of looks like, well, it has tentacles corresponding to the cusps of this fundamental region. And so, I don't know, it has about n different cusps. Something like this. Okay. Okay, so anyway. and then you have some whole big body coming out. Okay, but it has all these tentacles. And so now I'm about to summarize 20 pages of analysis by saying, so first of all, inside each of these cusps, so what's hard, of course, is that these cusps could sweep lots and lots of integral points. But what you show is that deep in these cusps, f, the invariant form is reducible over Q. So it's the kind of argument I've talked about before, but in this case it's a lot different because not every set of invariants have a lift, and that sort of complicates the geometry of numbers a bit. Reducible means that it factors over Q. Yeah. Far enough in the cusps, then the corresponding binary form associated to AB will factor over Q. And so you don't need to count them. And now if you sort of cut them off and you let the height go to infinity, then the number of lattice points in here will grow like the volume of this region. And the reason is because the analysis shows that you don't have to go look at points too far inside the cusp. So this region is fairly round that you're counting in, and then you can apply the usual Riemann integration kind of argument. And so basically what that says is that the total number of points in this fundamental region grows like the volume of this region. And so, okay, so that was a quick summary of the 20 pages of analysis. But I'll tell you, so the theorem is that the number of AB in VZ up to the action of GZ, okay, so these are pairs of symmetric matrices, right, up to the action of GLNZ, having height less than x, and such that the binary form associated to AB is irreducible over Q. Okay. It doesn't factor over Q. Grows like the volume of this region. And so it's a constant times how fast it's scaling when the height goes up with x. Right? So how fast does it scale? Well, it scales like x to the n plus 1. And why is that? Well, so x to the n plus 1 is, of course, the total number of binary forms of height less than x, right? Because they're n plus 1 coefficients of a binary form. And it turns out you get n plus 1 here, too, for the total number of A, B that have height less than x. And the reason is that how big is each variable inside the matrices A and B? Well, it's about x to the 1 over n in size, right? Because when you take the determinant, you'll get x. So each variable has x to the 1 over n, goes up to about x to the 1 over n. Right, once you've cut off the cusp, then it's sort of bounded. All the variables are bounded by a constant times x to the 1 over n. And then how many variables are there? They're, well, A and B are symmetric matrices of n by n size, so each one has size n times n plus 1 over 2. So the total number of variables is n times n plus 1. And then, so that's why you get the n plus 1.
How much is the analysis of the cusp response to your estimate about they play a role or they don't play a role?
They do, yeah. They play a role in the error term. So I should have said, yeah, so the cusps contribute an error term. And so a lot of the work is showing that cusp term is not bigger than the main term. That's where all the work is. And you can get a slight power saving. So x to the n plus 1 minus 1 over n times n plus 1 is the saving I'm able to get. And that's a contribution of the cusp.
So to improve that, you have to somehow...
Oh, no. Well, this is a lower order.
That's a lower
Yeah,
order.
so this is what you have to improve, actually. Right. So I'm not done yet, because this doesn't give the theorem yet, right? Because this C, turns out this C is about 2 to the n plus 1 in size, where the implied constant is independent of G. And how many binary forms do you have if height at most x? It's also 2 to the n plus 1 times x to the n plus 1 G. So what this is saying is that total number of AB right up to this G of Z equivalence is on average, okay, right, giving F is a constant on average. And that's not good enough for us, right? Because, well, this constant could be like 1 for each one, and then it's not saying that you don't have rational points. So something has to be done to get rid of some of these AB. And here's how you get rid of some AB. You observe that the matrices I wrote down are not general AB. They have a very special shape. And so we don't want to count all ABs in V of Z, but you want to count only those that can possibly have this shape. And to have this shape, you have to locally have such a shape. And already locally, it's very hard to have this shape. So I wonder if I can, maybe I'll write the last thing over here. So here's the thing, that even over R, so let F be an irreducible binary form. Okay, over Z. Irreducible means it doesn't factor over Q. And let R infinity be the number of real roots of, say, f of x1. Well, let's assume f0 is not 0, just to make this easier. Okay. Be the number of real roots of f of x1, and let R sub p be the number of factors of f mod p. Okay, then over the reals, one can count how many g of r orbits there are on V of r that have a fixed binary form. And that count turns out to be, so then turns out there are 2 to the r infinity minus 1 orbits of g of r on V of r. So having binary form f as its invariant binary form. And of these orbits, if you just examine all those orbits, so you can explicitly write down all these orbits, you examine those orbits. Of these orbits, only r infinity plus 1 have elements of shape this. So they call it a star. Have elements of shape star. So the other orbits just don't even have anything where all these kinds of zeros and stuff going on. So very few of the orbits, there are many orbits, especially when R infinity starts to get big. Only some of them can have elements of this shape. And then mod p, there are p minus 1 orbits. So on V of fp. So giving rise to f, and only rp plus 1 of those have elements of shape star, have star type elements. And so now what one has to do is in this count, we only count AB that at least locally can possibly have such a shape. And that's some real conditions, and that's some p-adic conditions. And that's enough to reduce. So here are the things that one would have to improve the constant. One would have to understand. So for example, this brings up the question of if you have a random polynomial of degree n, what is the expected number of real roots? But it's asking something more than that, because you want to weight. You actually want to weight the polynomials that have r infinity real roots by r plus 1 over 2 to the r minus 1. So you want to understand the expected value of r plus 1 over 2 to the r minus 1 for real polynomials of degree n. So if r is the number of real roots, you want to understand the expected value of the random variable 2 to the r minus 1 over, r plus 1 divided by 2 to the r minus 1. And that's why And then the same thing you have to do p-adically. I just said it over FP here, but you do better if you do it p-adically. And so you get those real integrals, and you get those corresponding p-adic integrals. You have to understand basically distributions of how things factor in large boxes, which is something that just happens to be what Terry and Ben have been thinking about from their point of view just recently. And so they're very excited suddenly when I just mentioned to them last night. And the finite fields and the real case, both of those cases came up for them independently in a different situation. So anyway, so this sifting to local orbits of the shape star reduces C to a C prime. And even just using just an infinite place is enough to show that C prime tends to 0 as G goes to infinity. But if you use all real and p-adic places, then it goes to 0 exponentially. So you can show that C prime goes to 0 exponentially fast as G goes to infinity. And that's what gives the main theorems that I pointed out at the beginning. Maybe in the last minute I'll mention, since Nick asked this at the beginning, so these are for general hyperelliptic curves. You can also look at special families of hyperelliptic curves. So for example, y squared equals, well, z squared equals f, where f is odd degree. So this corresponds to hyperelliptic curves with a marked rational point, namely a marked rational Weierstrass point. So this is a case that we actually studied before this one. So this is in joint work with Dick Gross. We show that most curves, so most such curves, have fewer than 20 rational points. And this was by somewhat similar methods, but it was involving averaging the size of the 2-Selmer group of the Jacobians of these hyperelliptic curves. So what we actually show is that the average size of 2-Selmer for these curves, of the Jacobians of these curves, is 3. And then we add Chabot-T because we get good rank bounds, and that leads to the result. But we applied a very weak form of Chabot-T, and this has been taken further in some amazing ways by Poonen and Stoll. So it took these average results on Selmer groups that we proved, together with, they went crazy at 2 adic Chabot-T. And so they actually proved that most, they could get it 20 down to 1. Have only one rational point. This is very recent rational point. Namely the Weierstrass point at infinity. And maybe the second thing I'll mention is where z squared equals f even degree, but monic. This case corresponds to hyperelliptic curves with a marked non-Weierstrass point, right? With marked non-Weierstrass point. Yeah, in fact, 2 such. Yeah, right. And in plus involution, right? And in that case, there's recent work of Schenker and which I think they're very close to proving that most have only those 2 points. don't know if it's there yet or it's close. It's very close, anyway. So such methods, counting methods also apply to certain families of curves. But the general case was harder to do because it's hard to get at the Selmer group because there isn't a base point to start with. And so this case was somehow very hard for a while. And what this construction allowed is allowed one to get straight to the points rather than having to go through the Selmer group. And that's what allowed the case with no points to happen finally. So, OK, so I'll stop there. Thanks very much.